All right, in this video, we're going to talk about some periodic trends, meaning we're going to look at the periodic table and see how different properties of atoms are changing as we look across the periodic table so that we can use it to help predict properties of different atoms as we go. You might remember from Gen Chem, you had the atomic radius that you had to learn, and it may not have made sense there, but hopefully by going over this a little bit more, we might remember these things and hopefully make a little bit of sense out of it. First trend that we're going to look at is that of the effective nuclear charge, and here we're going to be looking at the valence electron effective nuclear charge. In the previous video, we were able to calculate the effective nuclear charge for any electron in an atom. Here we're just generalizing and saying, hey, when we're looking at the valence electrons in an atom, how does the effective nuclear charge change on the periodic table? And really, the way to easiest understand this is to think about fundamental physics here. We can think about the force between two Coulombic charges, for example, a proton and an electron, Q1 and Q2 here, and how they're connected by radius here. And that's what really governs what this is going to do here. And what we see in our effective nuclear charge is a pretty simple trend that we see the increase of effective nuclear charge increases as we go down the periodic table, or if we go to the right here. What we find that is by going down the periodic table, we're adding large amounts of charge to our system. The nucleus is increasing by 10 or 18 electrons at a time here. And that's a lot of charge that we're increasing now. And so our shielding electrons just can't keep up with it in essence. Same thing when we go across the periodic table. Here, remember, the shielding electrons that are in that same shell weren't as effective. So as we go across a row here, we see that, yes, we are still going to be increasing that effective nuclear charge because now we have more atomic charges, and our shielding effect is not as good since we're dealing with that same quantum number n. So this is the trend that we'll see. And remember, what it's telling us, it's about the connection, the force between that proton core and those electrons in the valence shell. That's going to be really important. What is the force that's going to be connecting that valence electron to the nuclear core? Okay, the first trend we're going to look at is that of the ionization energy. And what that's meaning is that we're going to start with an uncharged atom in the gas phase, so a neutral species, and we are going to go to where we have formed the +1 ion plus an electron. That's the reaction that we're doing here. We should note that this is always an endothermic reaction. It takes energy to pull that electron away. It doesn't naturally want to go. So what I'm plotting here now is the ionization energy on the y-axis versus the atomic number on the x-axis, and we can notice some really important features. We have helium, neon, argon, krypton. Very quickly, we recognize that as we go across a row, we see that the highest ionization energy is given to the noble gases. Where if we are looking at the bottom side here, our lowest ionization energy is held by the alkalis. Now, why is this? This connects right back to effective nuclear charge. So if we remember, as we went left to right on the periodic table, as we got to the far right-hand side, that's where we saw the highest effective nuclear charge. That's also where we see the largest ionization energy. This is because now we've got that high charge. There's a strong force here, so it takes the most energy to remove that electron. Whereas when we're thinking about the alkali metals, they're the farthest to the left. They have the lowest effective nuclear charge, the least amount of force between those two. So it's the easiest to remove that electron. So basically, ionization energy can be projected by the effects of the effective nuclear charge, which is pretty cool. There are a few blips along the way as we're looking at effective nuclear charge and electron configurations and ionization energies. So, for example, I'm highlighting here for the moment a couple little disconnects in here that don't follow that trend. So, for example, beryllium to boron. Well, let's look there. When we go from beryllium, we have a full 2s shell versus boron has a 2s and then that singular p electron. So what we see here is that it's actually easier to remove that singular p here. Once we do that, we have now an empty p shell and a completely full s shell. So that's actually more stable for us. Let's look to see how this continues. When we look at nitrogen versus oxygen, nitrogen, we see that we have a half full shell versus with oxygen, there's one extra electron from that half shell. So when we remove that electron, we come back to a half full shell, which is going to actually increase our stability. Half full shells and completely full shells are more stable overall than partially filled. We see the same type of trend if we go down by a period. We see that magnesium to aluminum going from 2s or from 3s to the 3p. Here we see the phosphorus to sulfur drop. This is the same that's analogous as nitrogen and oxygen. So it's all connecting to what is the structure and symmetry of our orbitals. Are they completely full? Are they completely empty? Are they half full? We can also see some interesting effects in ionization energies if we look at more than just the first ionization energy. What I mean by that is if we look at the first ionization energy, that's just losing one electron from the neutral. We could go on to form the second ionization energy if we take that ion now, make it an M2 plus ion in the gas phase by removing another electron. We could also do the third ionization energy, where now we're going from the M2 plus to the M3 plus. So you kind of see what type of pattern that we're building here. Let's see what actually happens in terms of the actual energetics here. First ionization energy is here in the first column, nothing crazy going on here. But let's take a look for the second ionization energy. The second ionization energy always takes more energy than the first, because now we're pulling an electron away from an already more positive system. Now there's more charge, more positive charge to hold those electrons. It does not want to get rid of that. So that's the first piece we see. But we can see that there's a staircase in this chart here. So let's see what happens along that staircase. When we go from sodium, if we go from the first ionization energy to the second, that's a huge jump. That's an order of magnitude. Why does that happen? So let's think about the electron configuration of sodium. So if we look at sodium, it has a 3s1 electron. And underneath that, if we remember, we have our neon core. So getting rid of that first electron says, hey, we're going to get rid of this s electron. Cool. So when we go to sodium plus, that's just now a neon core. Now we have to remove core electrons. They are much more tightly bound because now we're much closer to the electron here. Core electrons are much harder to remove. And we can see that showing up in our ionization energies. So for magnesium, it has a 3s2 configuration as its valence electrons. So when we try to remove the third electron, that's removing the core electron, it takes a huge amount of energy. So we can see some basic things showing up there in terms of our trends. So there's a lot going on with ionization energy, I guess is my overall point here. Next trend we could think about is that of the electron affinity. And admittedly, electron affinity is a little bit more complicated. There's a lot more going on behind the scenes that we're not going to worry about here. But it's kind of the same process as ionization energy, but in reverse. So here we're starting with a gas phase neutral, but now we're adding an electron so that we can make the anion, the M- ion. And we can see that generally, this is an exothermic process. So adding an electron generally releases energy. But not always, and there's some specific places where we see that that's happening. So for example, if we look at beryllium down here, but let's think about the process here. If I'm adding an electron, what am I doing? For beryllium, to go to beryllium minus, we would be going from 2s2 to 2s2 to p1. So we're adding an electron into a higher energy orbital that takes energy. And we can see those types of things happening across the board. For example, over here we've got nitrogen. Just with a reminder of nitrogen, it has 2p3, and we'd be saying, do we want to go to a 2p4? What's going on here? Well, we've had to double up and pair electrons, so that's going to be a less favorable process. So that's kind of the quirk that we see here, but generically, with those minor things in mind, we could see that generally across the board, we are getting our highest electron affinities, or the most negative electron affinities, rather, at the top of the periodic table, and the most negative is going to be to the left here. So that is what we're going to see here. Again, this one's a little bit more quirky, a little bit more challenging, so this is about the level we're going to deal with electron affinity. Last trends we're going to talk about are with respect to size, and this is the one that can be a real pain in the butt because it makes a little bit weirder sense. I mean, going with atomic radii, the one that makes sense to us is going down the periodic table, we get bigger. Yeah, we're adding a lot more electrons. We're adding shells of electrons, so we would expect it to be bigger. The one that's a little bit quirkier is it increases going right to left, which might feel backwards because we're actually adding electrons in the opposite direction. So fluorine has more electrons than, say, oxygen, but we see that its size is smaller than oxygen. Well, why is that? Well, where we come down to this is we look at the effective nuclear charge of fluorine is going to be greater than the effective nuclear charge in oxygen on those valence shell electrons. Okay, so that's the trend that came before. How does that impact here? Well, now remember, since we have a higher effective nuclear charge here in fluorines, that's pulling those electrons tighter. So when I'm thinking about my electron interacting with the core, it's being pulled in more because there's more charge that it's seeing. So by understanding that effective nuclear charge, it rationalizes why we see the decrease in size as we go to the right here on the periodic table. It's a little bit weird when we first see it, but remember, it's because of this effective nuclear charge that we're seeing increasing. And our final one that we're going to look at is that of the ion size now. And really what we should recognize is, what do we see happening? So for example, if we go from lithium to lithium plus, we see that it has decreased in size by quite a bit. And that is true for all of my cations down here. So cations get small. They're always smaller than the neutral. But if we look on the other side here, we see that we have things like oxygen, which goes and gets bigger when it becomes an anion. This is true for all anions. So anions get bigger compared to their neutral. That's the trend that you need to know here. But think about, again, it comes back to really understanding what's happening with the effective nuclear charge here. When we're looking at our cations, we have more charge to deal with. So they're pulling on those electrons more tighter. Whereas when we're dealing with our anions, there is more negative charge, more repulsive, less for those, so more electrons that have to be accounted for by that nucleus. They can't hold them as tight because there are more of them. And it all comes back to that effective nuclear charge argument. All right. So a lot going on in this video. Sorry, it's a little bit on the longer side, but there's a couple trends that I wanted to go, and they all just kind of fit together. So that's the video we got here. All right, so take a look at these, make sure they make sense. If they don't, we'll talk about them more in class. If you need clarifications, obviously get a hold of me. We'll make sure we go through all this together. And until I see you next time, be excellent to each other.